Hi, my name is Adam. I'm hoping that this will be the first video of many more. If you're seeing it, then hopefully I should have all the videos already posted covering higher level Maths Paper 1 and Maths Paper 2. But this is going to be the very, very first one. So yeah, I'll just start right now. So the first chapter for your Leaving Cert Maths, I'm just going to work in chronological order with a lot of books that are out there. So I should have these labelled properly so you can go from section to section. So yeah, but I think the simplest one to start off with, and the first one in my book that I have, is just based on real numbers. So I'm just going to go over what a couple of different definitions are. So what is a real number? So a real number this is any number. So when I say any number, what I mean is whole numbers, it can be fractions, irrational, etc. So something like 1, 27, pi, 3.267. On. So a real number is just basically all numbers. Now there are complex numbers, but for the time being, assuming you haven't done that yet, you can just take that a real number is just any number you can think of. Okay, so that's your real number. Now on to natural numbers. So these are also just definitions, so you just need to know these. Now hopefully you won't need to learn them off. It'll be a case of, because you've seen them so often, you'll just remember it. But these are things you will need to know going in. So natural numbers, you can just think of it as, if I asked you to start counting, what would you do? You would do 1, 2, 3, 4, 5, on. So they're just counting numbers. That's all there. Okay. So just counting numbers. Just if you're counting them, what would you get? Okay. What about prime numbers? These are numbers that only have two factors, itself and 1. So examples would be 2, 3, not 4, 5, 7, on. Okay? The reason is because 2 can be written as 1 multiplied by 2. 3 can be written as 1 multiplied by 3. 5 can only be written as 1 multiplied by 5. Okay, but for example, 4 can be written as 1 multiplied by 4, but it can also be written as 2 multiplied by 2. Okay, so that's a prime number. And 1 is not included. The reason 1 is not included is because in some high level maths, you basically just get that theorems become less powerful if you include 1. So that's the only reason that 1 is not a prime number. There's no, physical meaning behind it. It's just that it it's convenient to let it be to let it not be a prime number, but it's also not a composite number. Now, if a number isn't prime, then it is composite. So composite, so if not prime, this just means it's composite. Okay, so examples would be something like 4, 6, 8, 9, 10, 12, on and on. So basically every single even number apart from 2. So 2 is the only prime number to remember, okay? Then you have other terms, such like your highest common factor. So your highest common factor is basically the biggest number that goes into two numbers. So for something like 6 and 3, the highest common factor is 3. Why? Because 3 goes into 3 and 3 also goes into 6. So the highest common factor is the biggest number that goes in, that's common to both. Okay, and then you have your lowest common multiple. So the lowest common multiple then, say between 7, I don't know, maybe 3. This equals 21. So it is the smallest number that both numbers go into. And in this case, it is 7. So 7 and 3 multiplied together give you 21. Now for something like 10 and 6, this is going to be 30. Okay? So you can think of it that 7 and 3 have nothing in common, and therefore typically it's going to be the answer of the lowest common multiple is just them multiplied together. 10 and 6 have 2 in common. Okay? So they both have 2 in common. So when I say that they have 2 in common, what I mean is that 2 goes into 6 and 2 goes into 10. And so in this case, if I do 10 multiplied by 6 to get 60. To get 60, I can then divide this by 2, and then I get 30. Okay? So that's another way of viewing these. Now you can also be asked to express a number as a product of its prime numbers. So if you are asked to express 240 as a product of prime, what you do is you start off with 240 and you divide in. You always start with the lowest prime number and go from there. So the lowest prime is 2. Does 2 go into this? Yes. So you start off with 2. 240 divided by 2 is 120. Next question, does 2 go into 120? Yes. 2 goes into 60. 2 goes into 30. Okay. Now 2 does not go into 15. So the lowest prime, next prime would be 3. If I chance 3 goes into 15, it goes in 5 times. And the lowest prime that goes into 5 is 5 because 5 is prime. This gives us that 240 can be written as 2, 2, 2, 2, 3, and 5. So I can just multiply all those together, I get 240. So now that's just writing as a product of primes. Now you can be asked to find, say, the highest common factor of 512 and 280. Okay, so first of all, for 280, we get this, Now, 2 doesn't go into 35, but 3 doesn't either, so the next prime then is 5. And then 7, because 7 is prime. So we get that 280 can be written as 2, 2, 2 times 7. Now for 512. I'm not going to bore you with this, but this is just 2 to the power of 9. Okay? So to find the highest common factor, you look at what is common to both 280 and 512. So in this case, there's 3 2's here, and there's also 3 2's here. So in this case, the highest common factor, the highest common factor is equal to 2 times 2 times 2, which equals 8. Okay, because 5 isn't common to 2, and 7 is also not common to 2 to the power 9. So the only thing that's common through both of those is that. Okay. Now, for the next thing to get the lowest common multiple. Now, so before, back up here, what I did was I looked to see what was common. I multiplied them both together and I divided by what was common. This is what we're going to do here. So you multiply them together. So 280 multiplied by 512 divided by what's common? 8. And this is equal to 17, 920. Okay, so hopefully that makes sense. That's how you get highest common factor and lowest common multiple. This is quite important for your basic arithmetic. So yeah, I would recommend learning stuff like this. Just to have it in your back pocket, but realistically, once you do a couple of questions, it should be fairly grand. Okay, yeah, that's that. Now, the next thing to look at is factorials. So what is a factorial? So if we have n factorial, this is n multiplied by n minus 1 multiplied by n minus 2 on multiplied by 3 multiplied by 2 multiplied by 1. So what this means is you just keep multiplying by n and then n minus 1 and n minus 2 all the way down until you get to 3, 2, and 1. So if we have 5 factorial, this is equal to 5 by 4 by 3 by 2 by 1. Okay. Also 5 factorial is equal to, this thing can be written as 4 factorial, so it's equal to 5 multiplied by 4 factorial. So you can also just take a 5 out, if you like. So that's all that factorial means. Now, one thing to again look at is that 0 factorial equals 1. Okay, this is again just convention. Please don't look at that and, be overwhelmed by it. All it is just a convention that you have, that basically just makes the maths easier. If you choose that 0 factorial is equal to 1. There isn't a specific reason as to why it is, but, some books will give a reason, but, it's not really. They could have chosen it to be anything they wanted to. So, it's specifically chosen to be that just to make your life easier. Okay, yeah. Now, what do we have here? There's a couple of questions that I could go over, but I don't think this part of the course is too hard, so I can leave that at that. So now I'm just going to go through what an integer is. So we had n for natural, now we have z for integers. Okay, so z is integers, and these are just whole numbers. Okay? That's all they are. So it's -3, -2, -1, 0, 1, 2, 3. So they go down to -infinity and they go up to +infinity. And just be careful. 0 is included. It's because a lot of people look at that and say, oh, 0 isn't a whole number and therefore it can't be included. But yes, it is. So that's fine. So yes, that is, completely fine. So yeah, that is your integers, and then you have your rational numbers. So rational then, which is q. These are just fractions. To give you the proper jargon, say q. So what this notation means is that q is a number in the set of the rational numbers. So this is saying that q is a fraction. So if q is a fraction, this is the same thing as saying that q can be written in the form of a over b, where a, b are both in z, where b is not 0. Because then we'd be dividing by 0 and that can't happen. And also you have that the highest common factor of your highest common factor of a and b equals 1. This may seem insignificant, but it's actually really important, because this we'll be able to prove, because of this, that root 2 and root 3 are irrational, probably in the next 10 minutes or so. So that, okay, never mind, we're doing it right now. So okay, so that's a rational number, and then you have irrational. This is just not fractions. Or in other words, numbers that go on forever and never repeat. Okay, so something like pi, e you haven't come across yet, but this is the natural number, or Euler's number as it's usually called, but there's no need to worry about it. You just need to know that it never ends. Okay, it just keeps going and going and going, and it never repeats. Okay, now something like a ninth, that equals 0.11111111. So see the way it repeats, the 1 repeats, and therefore I can write it as a fraction. So if ever a number repeats, you can write it as a fraction. Always. Okay, now there's also now, which is quite important, which is proof. So proof, root 2 are irrational. So root 2 and root 3 are both irrational, and we're going to prove it. So I'm going to do a proof So I'm doing a proof by contradiction. So this is basically when you start off and you assume it's true, and then in assuming it's true, you basically end up with a contradiction, and therefore what you assume to start off with must be incorrect. Okay, so I'm going to use the root 2 and root 3 to be irrational are the exact same thing, because which they are. Also, this can come up in the leaving cert. So either do your best to understand the proof or learn them off. So for root 2 to be irrational, so what I'm going to do is you're going to start by assuming that it can be written as a fraction. So assume root 2 can be written as a over b. This implies that 2 equals a squared over b squared. Okay, so just squaring both sides, I get this. This implies that a squared is going to be 2b squared. So I'm multiplying both sides by b squared to get rid of my fraction. Okay, now this is when you kind of have to think about it. But what you get is that because a squared equals 2b squared, for b is going to be a whole number and so is a. Basically, this implies that 2 is a factor of a squared and therefore also a. Okay, now why can I say that? The reason I can say that is because, well, assume it's not. Again, we get b squared is going to be a squared over 2. B is an element of z, and therefore b squared is a whole number, and therefore this thing must be a whole number. And just for instance, if a was odd, so I just assume it was 1, and I get 1 squared over 2, that's a half, and that's not a whole number. So the only way that it can be a whole number is if a is even, and therefore 2 is a factor of a. Okay? So therefore, we can write that a is going to be equal to 2k, where k is an element of z. Alright? So once we've established this, we can plug it back into the formula and get 2k squared is going to be 2b squared. This gives me b squared equals 2k squared. And now we have the exact same thing. Okay, so up here, we have this. And now we have this. So it's the exact same equation. And therefore we can conclude the exact same thing from it. So up top, we said that, a must be even and therefore it can be written as 2k. B now must also be even and therefore b must be able to be written as some 2l, where l is an element of z. But here we have a contradiction, and this is kind of a cool little thing that you can draw. This will impress your math teachers. This is the symbol for contradiction. Now, how is it a contradiction? We assume that a have no common but here we just showed that a and b both have 2 in common. Okay. Yeah. So basically what you get, so you just get that you get a contradiction and therefore a and therefore 2 root 2 is irrational. And then for root 3, swap 2. There we go. So for root 3 it's the exact same thing. Now for the construction, of root 2 is quite easy. Draw a line segment of length 1. Draw another line segment of length 1. At a right angle to each other. This is also 1. And remembering Pythagoras, call this h. We get that 1 squared plus 1 squared equals h squared. 1 squared plus 1 squared is just 2. And this means that h equals root 2. So the reason that this is quite weird is because we just said a minute ago that root 2 is never ending. So it never ends. But yet I'm able to draw it. So even though a number goes on forever, its length is still finite, which is quite fascinating. And now for root 3. Root 3 is a little bit more involved. I'm going to make the drawing a little bit smaller. But you start off making a line segment of length 1. You make a circle of radius 1, like this. Where the center of it is A, I call this B. Now you're going to make another one where the center of this is now B. Both those are 1. And what you have is that this distance here, this is 1, this distance is a half. This, again, using Pythagoras, say it's L. We get that 1 squared equals L squared plus a half squared. So we get L squared equals 3/4. So L equals root 3 divided by 2. And so this length here is root 3 divided by 2. Here is also root 3 divided by 2. And therefore this length here is equal. So that is how you construct root 2. Okay, so that is that. And now the next thing is going to be rounding and then scientific notation. So rounding, an awful lot you will get round to 2 decimal places. So what does this mean? This means if you have a number whatever number of decimal places you want, so in this case it's 2. So this is the only number you care about, okay? But what's really important is the number after it, okay? Now, why? Your question is this number closer to 2.79 or 2.78? In this case, the answer is 2.78. So if this number here, if this number is a 5 or more, you round the second decimal place. So the 8, you round that to a 9. But in this case, because it's 4, 3, 2, 1, or 0, you round it down. Okay? Hopefully this should be grand from leaving cert and make all sense. If this is the 3 decimal places, I do 2.784 because following the 4 there's a 3, and that's less than 5, and therefore I round down, and so on and so on. Now, scientific notation. A lot of people don't like this. But it really isn't too bad, I personally don't think. So, the idea is, let's say you have this, and you want to write this in the form of A n is an element of Z, and less than 10. Okay. Okay, that should be this. Okay, sorry, maybe your book won't have that. But yeah, you want it to be written like this. So you want the size of A to be between 1 and 10. So if there's a minus there, you just bring the minus out and act like normal. Okay. So in this case, what you do is where you identify where your decimal point is. Now for a number that has a decimal point, it's very obvious. But in this case, I'm just going to draw it. I'm just going to add it at the end. Okay. I'm just going to add another color. What would be visible? Maybe this. Yep. So what you now do is you say, okay, grand, there's my decimal point. Where do I want my decimal point to be? I want it to be here. Why? Because if it's there, then what happens is 9.8, that's less than 10 and bigger than 1. Okay? So that's where you want it to be. So now you ask the question, okay, how many moves does my decimal point have to go? So in this case, the answer is 5. So the answer is 9.8 multiplied by 10 to the power 5. Okay? And so if the decimal point moves to the left, then if it moves to the left by 5, then it's 10 to the power positive 5. I might just put a plus there just to emphasize that it's positive. Now, if you have the opposite, so say you have 0.0000056, in this case, you know where the decimal point is. Now, where do you want it to be? You go to the first non-zero number, which is a 5, and then it must be 5.6. Why? Because 5.6 is less than 10 and bigger than 1. If I put it at 0.56, I'm less than 1, so it can't be that. And if I put the decimal point after the 6, I get 56, which is bigger than 10. So that's why it's here. Now, how many places does it move over? In this case, it moves over 1, 2, 3, 4, 5, 6. It moves over 6 spaces, and therefore the answer is 5.6 multiplied by 10 to the power. Okay, now it moves to the right. If it moves to the left, it's positive. If it moves to the right, it's negative. So negative 6. Okay, and that's it. That's all scientific notation. Okay, that's all you do. It's also called standard form of time. And then finally, you could be asked for the order of magnitude. The order of magnitude is just this number. So if they ask you for a difference of order of magnitudes, so what's the difference in the order of magnitude between the first number and the second number, you would say it's there 11. Because you do 5 minus 6, which is 5 plus 6, which is 11. And that's where I got the 11 from. Okay. So that concludes the first video on real numbers. Hopefully it wasn't too bad. And yeah, that's everything. Thank you so much for listening, and yeah, thanks so much.